Okay, I think we are now live. Hello, everyone, and welcome back to the quantum computing workshop series with DoraHacks. My name is James, and I'm just going to give a quick introduction to DoraHacks before we get started, for those of you who may not be sure about what we do here. So DoraHacks is a leading hackathon organizer and developer incentive platform focused on the areas of blockchain, quantum computing, and space tech. And as part of that, we have this workshop series. So I'm very glad to have joining us today Professor Stephen Girvin. And I will get over to him to do the workshop first. But first, I want to touch on a couple of grant programs that we have at the moment that are based on the theme of quantum computing. So the first mini grant program is the NISC Quantum Grant, which we'll have a link posted into the chat if you're interested in that. If you're working on a quantum computing project or doing some research in that area, this grant could provide support. So you can reach out to us directly or submit your details on the grant page to see if you're eligible for a grant to support your progress there. And we also have the Frontier Tech Community Grant, which is a slightly more general grant, but it is available year round. And it's to show that we're strong advocates for hackathons in the areas of quantum computing, especially. We've been doing hackathons for over a decade. And so communities and organizations that work in the field, specifically organizing hackathons, can apply for a community grant there to support them with organizing the hackathon and any other meetup events. So links to both of those grants will be in the comment section and below the video. So please check them out and check out the other hackathons we've got on DoraHacks.io. We've done a number of past hackathons in the area of quantum computing, such as the Yale University quantum computing hackathon called Why Quantum, which was their first ever of the kind, and San Diego State University's Aztec Hacks 2024. So please check them out, those hackathons out and the grants if you're interested. Links, as I said, will be in the chat. And I would like also to encourage any audience members, if you're tuning in live, feel free to ask any questions you have for Professor Girvin in the chat. We'll have a Q&A section at the end. So any questions that are asked in there, I will ask on your behalf to Professor Girvin. But I will be quiet now and hand over to Professor Stephen Girvin. So thank you so much for joining us. Stephen is the Eugene Higgins Professor of Physics at Yale University and co-inventor of the superconducting qubit. So Stephen, we've been really excited about this workshop today. Thank you so much for joining us. I'll hand over to you now if you can just introduce yourself a little bit further and then go ahead with the workshop. Thank you, Stephen.
Sure. Thank you very much, James. It's a pleasure to be here and speaking to everyone. I'm a co-inventor of one kind of superconducting qubit, not all of them, the transmon qubit, which is in wide use. I'm speaking to you from the Yale Quantum Institute today, where we have a wonderful group of theorists and experimentalists working to advance quantum technology. So this talk is going to be for beginners, and I'll welcome, it's a very general, high-level talk, but I'll welcome questions at any level at the end. So what I want to talk about today are the grand challenges that we're facing. In the last 25 years, we've gone from quantum information processing being a complete pipe dream to, early stages of industrial success and building moderate scale quantum processors using all kinds of technologies, cold atoms, trapped ions, superconducting qubits, and so forth. And we made tremendous progress in the last 25 years, but we face very, very important challenges before this technology will become scientifically and economically useful. And I want to talk about those today. giving you just a general introduction to how all of this bizarre technology works. So let's see. So we're in the midst of a second quantum revolution, but let's start by describing the first quantum revolution, which took place in the first half of the 20th century. The people who invented the quantum theory, which is one of the most successful, perhaps the most successful physical theory in all of physical science. These people were thinking about the strange fact that the color of light emitted by atoms, if you put it through a spectrometer or a diffraction grating, you could see distinct colors. And they turned out to correspond to atoms having quantized energy levels. The energy can't vary continuously, but it can jump discontinuously from one level to another. And the color of the light that's emitted was related to the energy difference in the states that it's jumping between. And this was very surprising. Completely overthrew the classical mechanics of Isaac Newton, and was quite shocking, but there were no conceivable applications of this whatsoever. And yet, the inventors of quantum mechanics did not foresee any quantum devices, any practical applications. Even the more practical people who invented the transistor and the laser, the atomic clock that led to the global positioning system, they did not foresee how these things would be used. So the second quantum revolution is based on a new idea, not a new theory of quantum mechanics. It's just that the quantum theory is so strange and counterintuitive that even though we could do very precise calculations with it and make predictions in agreement with experiment, we did not fully understand all of its aspects. And the very strangest aspects that when you repeat an identical experiment many times in a row, you don't always get the same answer, that the answer can be random, and that certain quantum systems can become entangled, and even if they're far separated in space, there's some special spooky connection between them. These strange aspects, predictions of the quantum theory, seemed like bugs that, why would you want to build a computer where you're uncertain what the value of the bits are, and when you measure them, you get random results? But it turns out it's now understood in the last quarter century or so that these are not bugs, but rather features that we can take advantage of to invent useful new technologies. So, there's now a second quantum revolution underway. And just as the inventors of the first quantum revolution and the quantum technologies of the transistor and the laser and the atomic clock, which produced the technological revolution of the 21st century, just as those inventors couldn't foresee all the consequences of those, I would say that we cannot foresee the consequences yet of this revolution. The people that invented the transistor did not foresee that the integrated circuit, did not foresee that every second of every day in the world today, there would be about 30 trillion transistors produced. So who knows where this is going to lead? They certainly didn't foresee that computers would be used to play music or speak to people around the world as I'm doing now via video. So we'll see where this goes. But we can think of the second quantum revolution as a sort of a stool with three legs. One of the legs is quantum materials, new materials that are being developed and created and invented, containing electrons and electrical properties that are fundamentally quantum in nature. Quantum sensing, you probably have heard that measurements are a strange thing in the quantum theory, and there's a special role of the observer. When you observe or measure a quantum system, it changes. And in the days of Einstein and Bohr 100 years ago, they could have arguments over not real experiments, but Gedanken experiments, because the technology wasn't there to measure individual atoms and individual quanta. But now we can do that, and we have a much better understanding of quantum measurements and the role of uncertainty and randomness in those measurements, and how to beat the Heisenberg uncertainty principle under some circumstances to pull very tiny signals out of noise. And there are two major experiments in the world today that use our knowledge of quantum measurements to do quantum enhanced sensing of tiny signals. One is the LIGO gravitational wave detector, which measures very tiny, tiny ripples in the fabric of space-time using quantum sensing. And the other is a dark matter search, which is the HASTAC project at Yale, which is searching for axion dark matter particles using the technology that was developed to build quantum computers out of superconducting qubits. The fact that quantum systems are extremely sensitive to tiny external perturbations and signals is wonderful if you're trying to build a detector to find those signals, but it's really terrible if you're trying to build a quantum computer where you do not want the answer to be affected by these external perturbations. And this is the grand challenge, I think, in quantum computing today, which I'm going to spend a lot of time on in this talk. So quantum information includes new ways of doing computing, new ways to perform simulations of processes in nature, in particular quantum processes, and also communication of quantum information. And finding ways to make all those processes not sensitive to these noise and external perturbations is a grand challenge for today. So there's a lot of hype in this field right now, which frankly I'm personally concerned about. The technology readiness level is not very high. There's, as I said, been tremendous progress. Industrial companies are building systems with hundreds and even thousands of quantum bits, but there's still the lifetime of the quantum information is not very good at this point, and the circuit depth or the number of quantum operations that we can perform is still rather limited because of this sensitivity to noise and perturbations. And I believe that while we're making tremendous progress, there's still going to be decades of basic research needed to create revolutionary new technologies that have, I would say, in principle, the possibility of being as impactful as the technological revolution of the 20th century, but it's still much work to be done, and young people are going to, I hope to encourage young people to help us learn how to solve all these problems. And I think for the sake of the field, it's important that we be careful in how we speak to the public and to governments about the fact that the technology is still in very, very early stages. So there are grand challenges that can be found across the full stack of quantum systems, from the hardware at the bottom to applications and software at the top. And at the bottom, the hardware is made of materials, and material science is very, very important in helping us learn how to build better qubits, use new materials, different ways of putting, let's say, trapped ions near a surface, that a metal electrode surface that produces noise that we need to get rid of, or a superconducting qubit that could be made of a different material that might have longer lifetime or less noise. Material science experts need to talk to experts who actually build the quantum devices. They need a feedback loop when the material scientists find some different process or a different way to characterize and measure the materials. They don't know how that translates or whether it translates into better device performance. So there needs to be a conversation back and forth across each layer of the stack. That conversation is complicated because people are highly specialized and trained in different areas and literally speak different languages. And so we need to develop abstractions to speak to the layers in the stack above where you are and below where you are, to simplify the essence so that it can be understood by people from different fields working on different aspects of the problem. Likewise, the people developing devices need to be able to talk to the people developing applications and software. We need abstractions to simplify the description of the device and its performance and its capabilities, so that compiler developers who are not physicists but software experts can develop based on an abstract device model, noise-aware error correction coding and compilation, develop benchmarks and ways to make sure that all of this is working, ways to tune up and improve algorithms. And all of this is the concept of co-design, where people from each layer of the stack, with each specialty that they have, are working together to find the optimal combination of materials, devices, modifications of algorithms, and so forth, to get the whole thing to work as well as possible. And it's quite a complex process, and success requires being able to communicate with a broad team that has a different background than you do, and that's quite challenging, actually. So the people that, at the top of the stack who are working on applications, they don't really want to know exactly what the electrons and photons are doing down at the bottom layer, but they want to have a sort of abstract picture simplified with a few parameters that describe the important characteristics of the qubit. How long do they retain the quantum information? What kind of errors are there, and so forth. People at the device layer want to have a more detailed physics understanding of the devices, and they want to be able to interact with people above them and below them in the stack, translating into different languages when they speak to different people working at different layers of the stack. That's actually quite challenging. So solving some of these grand challenges is going to require a real interdisciplinary team. There's control theory, coding theory, computational complexity, people that know about networks, systems, information theory. You know, I'm a theoretical physicist, but I work closely with experimentalists developing quantum machines. But we physicists are not really systems builders. We don't, you know, we do experiments. We don't build systems that are online and working 24/7 and easy to interact with and highly reliable and so forth. So we need people from computer science, from material science, electrical engineering, physics, quantum chemistry, applied physics, quantum optics, and so forth. And you know, there's many interesting challenges. So typically, we imagine that a practical quantum computer will consist of a quantum processing unit, a QPU, which you can see over here in the right-hand side of the slide. There's going to be extremely rapid, on nanosecond timescales, signals input-output from the quantum processor, which have to be processed by a very large, very powerful, extremely fast classical processing unit that involves analog and digital microwave electronics, floating point gate array systems, extremely fast decision makers, chips, RF systems on a chip, all kinds of fancy classical computation and classical signals processing, very tightly coupled surrounding the quantum processing unit. So it isn't just a quantum computer, it's a massive system with a kind of quantum accelerator piece that's talking to a massive classical computer. So it takes many different skill sets to put all of this together and build a working system. And so there have been conversations in the US about how you build a quantum engineering undergraduate program. And this was published in IEEE Transactions, and you can also find the report of this committee that I was on here on the archive. So it gives some thoughts on how to start training people for this extremely interdisciplinary ecosystem that we need to build in order to make all of this technology work. Okay, so there are a number of grand challenges that I'm going to talk about. One is in theoretical quantum computer science, and it's a pretty basic challenge. We don't fully understand yet what powers quantum machines have, assuming they're ideal and don't make any errors and work perfectly. What powers would they have? And we have some understanding of this. We understand that the fact that quantum information processors can be, in some cases, for some problems, vastly more powerful than traditional computers, that is, that the hardware actually makes a difference, has overturned the foundations of theoretical computer science established a century ago. Theoretical computer science says that if you have a universal Turing machine, a universal computer, it can, if it runs Python, you could use it to write a compiler so that it'll run Fortran, or it'll run C++ or whatever you want. And different computers have different clock speeds and so forth, but fundamentally they're all the same, and any one can imitate any other, can simulate any other. So the hardware doesn't really matter. Some computers will be twice as fast, or the so-called polynomially equivalent. They basically have the same power. And we've learned how to classify the difficulty of certain computational tasks on traditional, what I'll call classical computers. So we know that multiplication of large numbers is easy. I can do it on my cell phone. But if I give you a very large number and ask you to find the prime numbers that, when multiplied together, give that number, that's believed to be hard on a classical computer. There's no actual proof, but it's strongly believed. And that asymmetry, that if I give you a large number and it's difficult to find the prime factors, but if someone claims they have the prime factors, it's easy to check by multiplying them. So that asymmetry, these sort of one-way problems, are the basis of public key encryption. For example, the RSA encryption algorithm that protects security on the internet. And a lot of the excitement about quantum computing began with Peter Shor's discovery of the Shor factoring algorithm, that a quantum computer, if it could be built, could solve the factoring problem very rapidly. It would have to be an extremely large, nearly perfectly working quantum computer, but it could break the RSA encryption. On the other hand, we also have learned now that if you transmit information using quantum bits instead of classical bits, you can actually enhance privacy. And even against an adversary that has a quantum computer, in the end, privacy wins out over sort of defense, ends up winning out over offense in the encryption area. It's also known that certain classes of problems are hard even for a quantum computer. Others are easy. So we know, for example, that solving the equations of quantum mechanics, which are very hard on a classical computer, are quite easy on a natural, on a quantum computer. But let's say finding the lowest energy state of a quantum system that's strongly interacting and has many electrons. For example, a drug molecule docking trying to dock on some target. Those can be quantum hard, or at least there exist instances in which that is hard, even for a quantum computer. Similarly, optimization problems that appear in logistics and finance and all over the place are probably quantum hard. On the other hand, people spend a lot of money and computational effort using classical computers to approximately solve optimization problems every day. Airline scheduling, Federal Express trucks, route optimization, all kinds of things. And even though computer scientists would argue that these are in the categories that contain exponentially hard instances, people have found very good heuristic algorithms to provide relatively rapidly pretty good solutions to these hard problems. And I'm hoping, one of the things I'm hoping for is that young people will start using quantum computers and develop heuristic methods, which we don't know what they are yet because we've only just now started using quantum computers. But we'll develop heuristic methods that work even though you can't prove that they should work, just as we do now with classical computers. So, we still don't have a good sense of what the killer app is that will offer quantum utility, assuming the hardware is nearly perfect. And the people that invented the first computers didn't realize ultimately what they were going to be used for. And I still think we don't know yet what quantum computers will actually be used for. But it seems likely that the first applications will be in quantum chemistry and material science, sort of having scientific value, and then eventually economic value. And as I mentioned, quantum heuristics for quantum hard problems is an area that I hope some of the young people listening today will help us develop. Another grand challenge is routing quantum information from one place to another within, from module to module, within a quantum processor, within what's called QRAM, quantum random access memory, between processors in the same laboratory, and ultimately between, quantum communication at the city scale and the national scale. Excuse me. And to do that, we almost certainly are going to need a way to convert the signals in, let's say, a superconducting quantum processor, which involve microwave photons, up to telecom wavelengths that can travel long distances through optical fiber. And so this transduction problem of moving quantum information across frequency domains that differ by a factor of 100,000 in frequency is a very important challenge as well. But now the biggest challenge of all is the quantum error correction problem and what's called fault tolerance. Fault tolerance is the ability to correct quantum errors, even though the quantum error correction circuit itself makes errors. And the fact that that's possible, even in principle, is, to me, really amazing, and in some way more amazing than the fact that if you had a perfect quantum computer, you could do quantum computation. So in a nutshell, here's the error correction problem. I'm going to give you an unknown quantum state. It's, I don't know what it is. You don't know what it is. I plucked it out of a quantum computer somewhere in the middle of the calculation. It's a very complicated state. I don't know what it is. And I give it to you and say, I want you to measure it to look for errors and then fix them. But if you measure it, it will change randomly due to this peculiar role of measurement and the observer in quantum theory. The state will randomly change due to what's called state collapse or back action. And your job is, if it develops an error, please fix it. So it seems completely impossible, but miraculously it can be done. And we're beginning to learn how to do it. So the way you do quantum error correction for an unknown state is to store the quantum information non-locally in a set of many physical qubits that make up a single logical qubit, as you see here on the left. And the information has to be stored non-locally in the quantum correlations among the qubits, because no single physical qubit can, know the state of the logical qubit. Because if the environment the noise or the environment sort of observes one of the qubits, whether it's in state 0 or state 1, that would then tell the environment what the state of a logical qubit is and collapse it, destroying the superposition of 0 and 1 that is the essence of quantum information. So you have to hide the information in some funny way, spread out among all these physical qubits. And then you need to be able to make special correlation measurements among multiple qubits to tell you about the errors that happen without telling you the logical state in which the error occurred. And quantum mechanics is quantum computers are kind of analog computers. Yes, they have bit values 0 and 1, but they can be in a continuous superposition of 0 and 1 at the same time. And it involves coefficients of numbers, quantum amplitude to be in 0 and quantum amplitude to be in 1 that can vary continuously. And there's a fundamental no-go theorem that analog computers cannot correct errors because every state of the analog system is a legal state. It's hard to tell that there are errors. But fortunately, you can make these special multi-qubit measurements which collapse the error state. Errors are continuous, but when you make this measurement, you either find there's no error or there's some discrete error. So measured errors are discrete or digital, and in this case, state collapse is our friend and allows us to correct those discrete errors when we see them. Now, we have an immediate problem that we've created one logical qubit containing n physical qubits, and each one of these n qubits is having errors. So the error rate is n times larger than when we started. So every quantum error correction scheme starts by taking a giant step backwards and making the errors n times worse. Then we have to build an error correction circuit, which physicists like to call a Maxwell demon, which does these special measurements, looks for the errors, fixes them, and sort of removes the randomness or the entropy from our quantum computer and puts it into a cold bath, just like a refrigerator does. And it has to be able to work very rapidly, and it has to not introduce any errors of its own, or at least not errors that it can't correct in the next round. And you can define a break-even point where the lifetime of this logical qubit is good enough that it matches the best lifetime of the best single physical qubit in the system. At that point, you've overcome that factor of n, but you're just back where you started. You haven't made things better. Beyond the break-even point, what we'd like to have is that the error correction is so good that it's 10 or 100 or a million or a billion times longer lifetime. And right now, we're in very early stages where the lifetime improvement is factors of 2 or 3. So it's above 1, but we still have a long, long way to go. This is a grand challenge. So you can show that if the error probability of the individual physical qubits, epsilon physical, is below a certain threshold that depends on the encoding you use, then the logical error rate will be that small number raised to a power related to what's called the distance of the code, how well it protects qubits. So we need physicists and electrical engineers and material scientists to make this physical error rate smaller. We need computer scientists and quantum computer scientists to help us find better codes that work for the particular noise that we have to make this error threshold larger so that this ratio is smaller. we need to be able to have lots of physical qubits per logical qubit to make this so-called code distance larger. And then we'll have a small number raised to a high power, which gives a very low logical error probability. And there's a subtlety to making the measurements that are needed to locate the errors without destroying the state. And there's been some recent progress led by my theoretical physicist colleague, Professor Shruti Puri here at Yale. And she's been working with us and with Jeff Thompson at Princeton, who's an atomic experimentalist, to think about these different kinds of errors and how to design code specific to them. So there's this sort of pyramid, a hierarchy of errors. There's leakage errors. So you have a qubit as a physical system that has quantized states like an atom. And we'll pick out two of them, let's say the lowest two levels, and call them 0 and 1. Those are our quantum bit states. But they always have other levels. And a leakage error is where you leave the code space, the space of 0 and 1 and linear combinations of them, and go into these higher levels. Those are the most dangerous kind of error. Then there are Pauli errors, where you can have bit flips, just like in a classical computer, but you can also have phase flips, the superposition of 0 and 1 changes, and that doesn't have a classical analog. These keep you in the code space, but they change the value of the answer. Those are bad, but they're less bad than leakage. And finally, there are erasure errors. An erasure error is a leakage error whose location you know because there's something about the system that raises a flag and says the error is right here. So you can do this process of erasure conversion by making some sort of measurement, perhaps, that says you're in the code space or you're not in the code space. And if it flags an error, that's called an erasure. And it turns out that if you know the location of the erasure errors, they're much easier to fix. You don't know you know this qubit has left the code space. You can put it back in the code space, but you don't know whether to put it back as a 0 or a 1 or some superposition of 0 and 1. So you almost certainly have a Pauli error after that, but you know where it is. And so that reduces the randomness and uncertainty in the problem. You don't have to make special measurements to find out where it is. You already know. And that those types of errors are much easier to fix. And there's a lot of interesting progress now being made in both superconducting qubits and atomic Rydberg atom qubits using these new ideas. So we're, climbing this staircase towards quantum utility or quantum advantage. And we're just entering the era of quantum error correction and beginning to be able to do operations on, with logical qubits. And hopefully soon we'll be running algorithms on multiple logical qubits and eventually have a large-scale, fully fault-tolerant quantum computer, which is going to offer advantage both for solving scientific problems and economically interesting problems as well. And I hope young people will be able to help us climb this staircase to success. So thank you very much, and I'm happy to take questions.
Okay, we are on the way. Thank you, Professor Stephen Girvin, for that wonderful workshop. Very, very interesting. I'm sure that's got everyone's thoughts racing. We've got a few community questions. Let me just check the chat. Yeah, I've got a few here just to tag on to the end of the workshop. So this is a question from Yu Shah. Would near-term quantum computing capabilities allow us to answer some of the unsolved questions in physics, be it quantum gravity or the Navier-Stokes equation?
Yeah, so that's a great question. There are, the answer is maybe. We certainly hope so. There are new ideas for algorithms, for example, that could be used on a quantum computer to solve partial differential equations that are very, very difficult, nonlinear partial differential equations like Navier-Stokes. There are quantum gravity. Okay, I'm far from being an expert, but there's this sort of story that is being told that is somewhere between a theory and an analogy, that quantum entanglement in some sort of fabric of qubits is a way of describing distances in the metric and space-time, and ideas for, resolving things like the black hole information paradox and so forth are coming out of this. And there's interest in performing simulations of the equations of quantum gravity on quantum computers. But at this moment, I would say it's kind of just an analogy, as I understand it, and not really a full-blown theory yet. And the scale of quantum computer we need to do something quite interesting is still currently beyond our reach. But it's certainly, I think the first important applications of quantum computers will be for these sorts of answering some of these scientific questions.
Okay, we'll have to wait and see then. Thanks for that. We've got another question from the same community member, actually. Would fault-tolerant quantum computers allow for a more accurate prediction of the financial market and stock prices?
So there's a lot of interest in the financial community on making high-speed predictions of stock prices and so forth, high-speed trading. There's certainly a lot of work being done, algorithms being developed, but I would say at this point, we're still not completely sure how much, at least I personally am not completely sure about how much quantum advantage there is to be had, but it's definitely a topic that's being extensively explored right now. But of course, it'll be an arms race. I mean, if somebody figures out a good algorithm and everybody starts using it, then that will affect the dynamics of the market, and it'll always remain complicated to make money in this competitive environment.
Sure. Okay. Thank you. We've got our next question from Bernard. It's a question about the differences between discrete variables, dv, and continuous variables, cv. It appears that the majority of research efforts have been directed towards dv, which operates on a two-level system. However, some groups and startups, such as Alice and Bob, have focused on cv and reported impressive results recently, including bit flip times exceeding 10 seconds. Could you please provide an overview of the pros and cons of dv versus cv approaches to fault-tolerant quantum computation?
Sure. So this is a good question. So discrete variables are qubits, and yet they have a continuous aspect. You can have a superposition of 0 and 1, the discrete basis states, that varies continuously, as I said earlier. But that's sort of the traditional quantum computing approach. the group here at Yale and many other groups, including the Paris group that's working on this startup, Alice and Bob, are thinking about the CV case. So the CV case is uses not qubits, but what are called harmonic oscillators, things that have an infinite number of states. It's a countable infinite number, but there's a sense in which it's described by a variable like a position, which is continuous. But anyway, it represents the fact that there's a very large Hilbert space dimension, many states. So there's a lot of interesting work going on to use continuous variable systems to encode a logical discrete variable qubit. These are called bosonic codes. They have a number of advantages, and so far they are the only system that has shown quantum error correction gain for memory operations. That is, the logical qubits living longer than the individual components that they're made of. They've all been bosonic qubits. In atomic physics, that's not a problem. You already have fantastic memory. The problem then is making errors during gates, and people are beginning to get error correction gain for gates as well. So there are a number of advantages. The many seconds, so-called T1 time, the bit flip time for these cat qubits that Alice and Bob have is very impressive, but that's kind of a classical measure of how good a qubit it is. You also have to look at the phase flip time, and you need it to also be large, and that remains a challenge. On the other hand, if you have a cat qubit like that has a high noise bias, that is very few bit flip errors, mostly phase flip errors, then having only one kind of error that's important makes it easier to fix. So the jury's still out, but that's a very interesting direction, which could prove useful. But the phase flip time is still very short for this case.
Okay, great. Well, I hope that answered your question, Bernard. We've got another one from you, actually. You'd like to inquire about error correction codes. Is there a theoretical limitation to the encoding efficiency? For instance, the efficiency of the surface code appears to be relatively low compared to that of the quantum low-density parity check code. Additionally, is it feasible to implement the QLDPC code in superconducting quantum computing platforms?
Yeah, good. So by efficiency here, I think that what is meant is the so-called rate. How many logical qubits are you encoding in a big collection of physical qubits divided by the number of physical qubits? So what if you had 1,000 physical qubits and you encoded one logical qubit? The rate would be 10 to the minus 3. The surface code encodes one qubit in an ever larger array of physical qubits. So its rate asymptotically goes to 0 for large distance codes. So that's not very efficient. The so-called quantum low-density parity check codes have finite rate. That is, if you had 1,000 physical qubits, some finite fraction of them get, like, let's say, 0.3 or something. That would be 30% of that number would be the number of logical qubits that can be encoded. So that's good. That's a higher efficiency. It comes at a price that the error checks that you have to do involve physically distant physical qubit, geographically distant physical qubits. Those measurements are much more difficult to do, especially in a superconducting system that has only near neighbor connectivity. There have been recent interesting experiments from the atomic physics world where they can literally move the atoms around to be near each other, and there's sort of more connectivity. But the one important question is, for these low density parity check codes, we're still just barely beginning to learn how to make those measurements and how to do gate operations. If you have 300 qubits, logical qubits, encoded in 1,000 physical qubits, and you want to do a gate operation on the 173rd logical qubit, that's not so easy. We're just beginning to learn how to do these things. There's a paper that's from IBM on a particular way, a particular low density parity check code that looks like it could be more feasible in a two-dimensional grid of qubits with not too distant connectivity. But there's still much to learn about how to actually implement these codes and how to do logical gate operations on all the qubits that they store. So atom systems may have an advantage there because you can move the atoms around. But right now they have a big disadvantage that when you make a measurement to look for errors, it tends to blow the atom out of the trap. And it's a destructive measurement. So every technology has, and every code has its pros and cons. And we're still in the middle of trying to figure all of this out.
Okay, thank you. And I think we've got time for one more question, which is again from Bernard, or Bernard. What are your thoughts on the ultimate scalability of superconducting qubit systems? Currently, it appears that considerable resources are required to establish logical qubits. In contrast, recent advancements in optical tweezer technology have enabled the trapping of over 6,000 atoms. Given the inherent properties of solid-state systems, do you believe it feasible for superconducting qubits to scale up to the thousands qubit range in the future?
Well, I mean, IBM has devices with 1,000 qubits, superconducting qubits already. But as I said, the connectivity is fixed and local. The Rydberg atom array people that have this ability to trap hundreds and maybe many hundreds of atoms in tweezer arrays and move them around. But each one still has their own difficulties. So at this point, I think it's unsafe to bet on which technology is actually going to succeed first, or maybe it'll be something completely new. There are just still huge challenges between this and full fault-tolerant quantum computing. We're still at the stage where people can do really impressive experiments that show off one particular aspect of their technology working amazingly well, better than anything else for the first time. But those experiments tend to be tuned up to do that one thing. And no single experiment can be right now tuned up to do everything that we need to do simultaneously to have a full stack, fault tolerant quantum computer. So I agree that there's a lot of exciting progress in the atomic world, and sort of a steep derivative of progress. The superconducting world is beginning now to think about how do we overcome this local connectivity problem. which is indeed a challenge. But on the other hand, when we measure one of our qubits, it doesn't disappear. So, you know, there are still many challenges in any technology, and I think your question is a good one, but I don't know which technology in the end is going to succeed first.
Okay. Well, thank you to our community members for chipping in with those questions, and a huge thank you to Professor Stephen Girvin from myself, James, and the DoraHacks team for taking the time to speak with us and give this presentation today. It's been one of our most highly anticipated talks in the space, so we really thank you a lot for that.
Well, thank you very much, and thanks also to DoraHacks for their help with the YHAC meeting here at Yale last April. It was pretty wonderful experience. And
Great.
thanks for this opportunity.
Yeah, brilliant. And just before we jump off, I just want to remind everyone in the audience that we do have those 2 ongoing grant programs. They're around all year, all through the year. So please do submit your projects or apply. And if you don't want to do that, just get in touch for more information. That's the NISC Quantum Grant and the Frontier Tech Community Grant. Links to both of those will be in the comments section. So check them out. The submission portals are always open. So feel free to reach out anytime for that. And make sure you stay in touch by following us on social media at DoraHacks, whether it's YouTube, LinkedIn, or Twitter, because we do have other workshops coming up in the future on this and other interesting frontier tech topics. So thanks everyone for tuning in. And one more thank you to Stephen Girvin. It's been an honor to have you here today, and we look forward to catching up soon.
Thank you.
Thank you.